Hello everyone and welcome. My name is Jason Gregerson and in this video we're going to talk about trig substitution. So what is trig substitution? Well, it's an integration technique we can use on integrals that look like this. Integrals where we have a quadratic function either underneath a radical or in the denominator of a fraction that makes it hard to simplify the fraction or the radical. So integrals where we want to use trig substitution are characterized by challenging quadratic functions. Now, how does trig substitution help us with those challenging quadratics? Well, trig substitution takes a sum or difference of squares underneath the radical or in the denominator, and it turns it into just one thing squared by using some trig identity. So in this example, I have the square root of 1 minus x squared, but if I replace x with some trig function, just the right trig function, I can then use a trig identity to turn this into the square root of one trig thing squared. And then it's easy for me to evaluate that radical. So what are these trig identities that we're going to use to help us simplify these quadratic functions? Well, one of them is our good old Pythagorean theorem here. Sine squared plus cosine squared equals 1. Now, if we just take that 1 that we all should have memorized, we just divide through the whole thing by cosine squared, we actually can generate the second equation we're going to need. Tangent squared plus 1 is equal to secant squared. Once again, we get that just by taking the previous one, dividing through by cosine squared. Now, if we take both of these and do a little bit of algebra, we'll get some new ones we need to work with. If I take tangent squared plus 1 equals secant squared, and I just subtract that 1 to the other side, I'm going to get this equation. Tangent squared equals secant squared minus 1. If I go back to that first trig function, trig identity, sine squared plus cosine equals 1, if I subtract sine squared to the other side, I'm going to be left with this guy. And this is really the one I want to work with. Why? Because this first equation tells me what to do when I have 1 minus something squared. The next one tells me what to do when I have 1 plus something squared. And the last one tells me what to do when I have something squared minus 1. And those are really the three situations I'm going to run into. So now that we have our three identities identified, let's look back at our square root of 1 minus x squared. Here I have 1 minus x squared. That reminds me of 1 minus sine squared. So what I want to do here is let x equal sine of theta. If I let x equal sine of theta here and I plug that in, I get 1 square root of 1 minus sine squared. But as I can see it from my trig identity, that's equal to the square root of just cosine squared. And I can easily simplify that to just get cosine. So by letting the substitution x equals sine theta and the associated trig identity, I can simplify this radical expression. And what if I had something like 1 plus x squared? Well, that kind of looks like that tangent squared plus 1, right? So in this case, I'd want to let x equal tangent of theta. And if I replace the x with tangent of theta, I get 1 plus tan squared, but my trig identity says that's equal to secant squared, which once again helps me simplify this radical, or maybe some other problem helps me simplify a fraction as well. One more case to look at. What if I have x squared minus 1? Well, that kind of looks like that secant squared minus 1 situation. So in this case, I'd let x equal secant of theta. I'd plug that guy in. I'd replace that expression of the radical with tangent squared, and now I'm able to take that square root. So the concept of trig sub says that we're making a clever substitution, x equals either sine, tangent, or secant, because when I plug it in, I'll be able to use the associated trig identity to simplify the radical. Okay. Now, let's bring that back into the process of integration and see this process all the way through. All right, so now I have an integral of 3 over the square root of 2 minus x squared. And I'm trying to integrate this guy. Now my trig sub steps here are first I have to ID the form. I have to figure out which trig identity I want to use here. That will help me choose the right substitution. So step 2 is let x equal some trig function. After that, I'm going to be able to calculate dx by calculating the differential of x. And then I'll plug all those theta values into my integral. I will then be able to integrate. And then lastly, I'm going to substitute back in to get to my original variable x. All right, so for this problem, I have a number minus x squared. It's going to remind me of that 1 minus sine squared expression, right? Now, I don't have exactly 1 minus x squared. I have 2 minus x squared. But luckily, all these trig identities, I could simply scale them all. So if I just multiply through my equation by 2, I can get this expression. right? So now I have 2 minus x squared. I really wish x squared was equal to 2 sine squared, right? So that kind of wish statement tells me the substitution I want to make. If I want x squared to be equal to 2 sine squared, I could then plug that value in for x squared to get this expression of the radical. And to make that substitution, I would let x equal the square root of 2 times sine theta, right? So looking at the trig identity helps me identify what the substitution I want to make. If I let x equal root 2 sine theta and I plug that in, I'll get this expression for my integrand. However, I still have to replace the dx portion of the integral. But if I know x is equal to root 2 times sine of theta, I can then calculate the differential, which is the derivative of x then d theta. Now if I replace dx with this expression, now I've plugged in all my theta values into the integral. Now I'm going to let the trig substitution process work its magic here. So now underneath this radical I have 2 minus 2 sine squared theta, but because of my trig identity, I know that's all equal to 2 cosine squared. So I can get that simplification from the trig identity. And now I can just look to simplify this guy algebraically. If I take the square root of cosine squared, I'm going to get cosine. Square root of 2 is root 2. So it looks like the numerator and denominators are going to cancel out here. And I'll be left with the integral of 3 d theta. So all this simplification has really made my integral much easier. If I integrate 3, I'm going to get 3 theta. And my last step is now to go back and replace theta with what it's equal to in terms of x. How do I do that? Well, I look to my original substitution. I know x equals root 2 sine theta, which tells me that x over root 2 is equal to sine theta. And my whole goal here is to solve for theta, so now I just need to take the arc sine of both sides. So it looks like theta is equal to arc sine of x over root 2. So if I plug that value of theta in, I can get my final answer in terms of x. And one last step, don't forget to add your plus c. And so this really wraps up this first example of trig substitution. I looked at my integral, I identified which trig identity it was related to. That helped me identify the appropriate substitution to make. So I then chose my x equals. I then calculated my dx. I plugged in all my theta values. I then simplified and did my integration. And lastly, I plugged my values of x in. All right, that concludes this video. Thanks for your time.